Actually, okay. What did you say? Oh, time.
Number 16.
Yes.
Time. Yeah.
Okay. So yes, this was about the. So all the solutions are like online, right?
Mm-hmm.
Okay, but they don't really go into detail.
Yeah.
Also,
explain it.
Yeah, and also Ron, told me that one of the solutions looked really weird.
Okay.
We can talk about that in a minute. It's the one with the aluminum, not this one with the aluminum plate, but
yeah, the sky and the ground. Is that the one?
No, it's the one with it's like a hot plate, and you put water on it.
Oh yeah, yeah.
And then the water evaporates or whatever, or vaporizes, and then you have to find the final temperature.
Right.
Anyway, we'll get to it.
Okay.
So so for this one has the power is plus I guess K of copper, right?
Mm-hmm.
Times A, which was the cross section of the copper rod, and then times this is dt dx, but actually it's gonna that I meant dx, but it's actually gonna be delta t delta x, and this is just going to be the length of the rod, so I guess I could just put L here. And then delta t is obviously going to be T2 minus T1 or whatever, or T, whatever the materials were, I don't remember what they're. There's a big one and a small one.
Copper, aluminum.
Yeah, copper, exactly. So you can, so obviously you have to know what the materials are, like aluminum and stuff, to do the radiation stuff. You don't have to know it for here. So if you can compute the power, so this is in watts. Right? I'll do this because it's not literally equal to that, but the units are watts. What we can do is say that a watt is a joule per second. So the energy that it has. So what we want to find is the time when it's a certain temperature, right? So the question asks for time for temp T. Right, that's the hard part because we know they ask you for the time when it's temperature T, and they give you the conduction equation for power. But how do we relate this to time? Because time doesn't really seem to appear anywhere here. Well, there was another. This happens like several times where they ask you for time. Like last semester, this happened a few times where they asked you something about time, and you had to use power as the only place that has time in it. So that's the big thing. So basically, E equals for constant power. Which it's, it's constant power, because these temperatures are the same. Oh wait, no, it's not a constant power. Well, let me just write this first. So P is integral of P dt. So this is just, normally we would write something like P times T. Because really, like, power is energy over time, right?
Right.
Deltas. So I guess we could write, so this is fine, except this is fine. But when we try to write it the other way, we're sort of assuming the power is constant. We don't want to assume that because one of the temperatures is not changing, right? But the other one is changing. So we have this. Now we know that E, which is the energy received by the aluminum, or whatever the one that we care about is, that's going to be equal to mc delta T, right?
The mass of the aluminum.
Mass of the aluminum. This is Al. This is Al, by the way. Yeah, Al.
Because it's changing.
Al, delta T, Al. And, right, and so now, I thought it was going to be a little easier. I thought if the power was constant.
You see where my question comes in.
Yes. So if the power was constant, of course, we could just plug that in here.
Yeah.
Plug this equation in here. It's just times T.
Right.
And that's equal to this, and then just divide this and solve for T. So now we technically have to do an integral.
Lovely.
Where everything is a function of time. So, not everything. The T I'll just say it's T2 is a function of time. Let's say T2 is I'll call it T of the aluminum. And then T1 is just the other thing, which is a fixed temperature.
Mm-hmm.
So now we should really have Ka, let's just set Ka. T aluminum, so K over L, I guess. T aluminum, which is a function of time from 0 to T. I'm not sure this is, well, let's see. Okay, equals MC AL. And now delta T is going to be the cumulative temperature change from the beginning. So it's going to be like TAL minus T naught AL, which is just the original temperature of the aluminum.
Mm-hmm.
I'm not sure that we'll need this to write all this out, but okay, and now well, I don't think we know how to do this because we don't know the differential equation.
Yeah, he said he used a MATLAB code.
So what?
He said in like the solutions, he's like, I used a MATLAB code, and I was like, I don't.
Let me look at the solutions.
Yeah, that's why I was like, okay, but how do you actually do it?
Right.
I don't care what code you use.
Which what number is this again? 16?
Yeah, this is 16.
Oh, you can use the average power. Okay, here we go.
Ooh.
He says you can use an average power to calculate the time.
Oh.
Well, I don't actually think that's true. That will approximate it, but that I don't believe that is actually true. Oh, more accurate would be to use an iterative loop. That's fine, but what's the... See, okay, hold on a second. Let me look back at his...
Because he does it at one point in here where he like multiply the power or something. I don't know what it is.
Can I see the conduction? Because so there's a thing called the heat equation, which is a differential equation, which tells you about how heat is transferred, as you might imagine. But and you need that to solve this. Yes, conduction. Okay, yep, it looks like it is not here. Okay, so I would guess, yeah, okay. Yeah, so we can't do it this way. So we can't do this because basically we need to know a function like this, right? To integrate, and this is how you get this is solving. It's called if you Google heat equation. There's a differential equation that tells you about heat.
Oh.
This is not a differential equation. This is telling you how power is transferred.
Right.
But it doesn't tell you like if it said power is constant. Then it would be a differential equation because of. It'd be something like this, and it would be a different equation, but it's not, and we don't have a rule about that. So, we could say instead we'll take the average power, delta T. So this is another we've used this before, right? We've used this same sort of form when we did the average force is how do we get the average force again? Or no, we did the work or something was like the average force times
Oh.
dx. Do you remember that we never, they would give you problems with work and stuff, and they would say, what's the average force?
Mm-hmm.
And the reason they say that is because you can't actually like do a division and find the force is actually a function of time.
Right.
So you can't actually find it at any specific time. It might have changed, but you can find the average because that's what it is. So yeah, so it's basically, in other words, you've done the integral and you've divided by this whole time. So it's like, anyway.
It's the average of it.
Right, exactly. So so it's the same thing as this. That this we can also use this equation, which is the average power,
Mm-hmm.
is the total change in energy over the total time.
Okay.
So we can do that here. So I guess that's by his comment. I assume that's what he wants you to do. Is this average power here
Mm-hmm.
is the total change? I should put delta E. Sorry, this is the first law, right? Of thermodynamics. So or it's this equation. I guess it's not really the first law, but anyway, delta E is the average power times delta T. Now the average power, we could say that we could just find, they ask you when it gets to a certain temperature, right?
Mm-hmm.
We could just find the final temperature. So find the power at, I'll do this. I'll say average power is going to be power at T final, right? Plus the power at T initial over 2.
Mm-hmm.
Right. And that is actually correct. I don't know why I'm hesitant. I feel like no, that's correct.
Too simple.
No, that is correct because it's linear and
Yeah.
TL. So yeah, so the argument in here means this thing, the
Mm-hmm.
aluminum temperature, right? Obviously there's many arguments, but if you just find the power, the average, or sorry, if you find the number of watts that flows through the copper when the final temperature is that they tell you is of the temperature of the aluminum, then find it for the initial temperature.
Yeah.
Just take the average of those two powers and you get the average power, and it actually turns out to be, that is exactly correct. Okay, so this is correct. It's not even, I thought it was like an approximation. This is actually correct. The heat equation should have told us that, although I don't know what it is. So anyway, and so this becomes, it is just P average delta T. And now, how do we do anything? Like, how do we solve for delta T? So that was all just this side.
Right.
The other key thing you need to know is that we need another expression for the energy, because that's obviously, we have an equation for the power,
Mm-hmm.
that's fine, but we want time out of it.
Right.
Well, the only thing we have two, it's like if you knew distance and velocity and you needed time, it's like, well, there you go. Like
Mm-hmm.
you have 2 out of the 3. So if you need time and you have power, energy must be the other thing, and so we need some other equation for the energy of a material that's at that changes its temperature.
Mm-hmm.
Well, we know that exactly. It's just mc delta T, right?
Mm-hmm.
And so that's just this thing. This is going to be final now, and this is going to be initial, right? Of the aluminum,
Mm-hmm.
and that would be the heat that the aluminum gains on being heated, and that's a value of the energy. But because we know all that heat, well, we don't know all of it doesn't come from. This is the heat gained by the aluminum. We actually, I guess, should probably also put the heat from the emission, or from the, what do you call it, the radiation. I guess you should also put this. I don't know if it really matters, as in if it's a significant number.
Okay.
So you don't know this actually either. You know the power. Okay, sorry. I meant, it should be on this side. So this is the power from conduction. But we also have, I forgot that the other part of it was the power from radiation. Also times delta T, the same delta T.
Mm-hmm.
This is also a thing has the temperature in it and stuff. And now this is actually going to be slightly different. So this equation is actually not true for the radiation because it has a 4th power of the power. I guess you could just take the average anyway, even though it's not correct. Okay, well, you could just do that anyway, that's fine. Well, yeah, that's fine. Just do that same thing to get the average power.
Okay.
It's not actually completely correct, but whatever. But anyway, so now you have these two pieces, right? This is the energy it gains from the radiation, which is like the net. You know how like when you find things in a thermal equilibrium, you say that the emitted radiation is equal to the absorbed radiation. So this is the net radiation average, and I think it's in like supposed to be in like a vacuum or whatever, so you don't have to worry about the one thing. Yeah, so you don't have to worry about the one. You've already done this, I think, for a different part, right? For the first part. So anyway, these two, the same delta t, of course. So you can just add these together, factor out delta t, and then you can just divide delta t over here, and that's it. So all we're doing is just saying that this side tells you about the energy change of the energy change and how it relates to temperature. They're exactly proportional with just mc. That's the change energy of the aluminum, internal energy, and the change of temperature of the aluminum, which is like this. But then we say what's causing that, and it's just these two sources, I guess. It's conduction and radiation. We have two formulas for it. Technically, we should really be always writing that E energy, change in energy, is going to be from T1 to T2 of P dt, and where P is a function of time. In this case, we don't know exactly how P changes over time. We know how P changes over temperature, it's just that equation. But we don't know how it changes over time because we don't know how temperature changes over time. And how temperature changes over time would be the solution to the heat equation, which is a whole other thing. But we can instead just use the average and use this equation, which is roughly equivalent to this for a linear P.
Okay.
And here it is linear, and the other one is not linear, but it's a Taylor expansion type that we use to approximate it. So we round the answers anyway, so nothing really matters too much.
Well, I did.
Yeah, and so he writes in the answer. I'm saying he because I believe it's the last TA. It might have been Christos. Actually, I don't think it is because I don't think it's writing. But anyway, I think it was the last TA that did it, or maybe it was like 10 years ago or something. But using average power and using an iterative loop, when he writes iterative loop, I'm sure he means he's literally doing the heat equation as a differential equation in MATLAB, which you don't have to do if you don't want.
Ever.
I don't. I'm sure if you Google MATLAB heat equation, you can find a thing that simulates it. Especially, you can probably find a cool one that does it in 2 dimensions. Because in 2 dimensions, not to get sidetracked, but
no, it's good. This is part of coming to office hours. Is the sidetrack tangent.
Oh, it's very exciting. You never know what's going to happen. So I had to do this in undergrad. We had to do this it wasn't with MATLAB. It was with some stupid, I don't know, C++ or something. But anyway, so we had basically you have a grid, and you had to write like a finite difference heat equation, and you had to start it where all the blocks were at 0 degrees, and this one was at 100 degrees or whatever, and then you could just run it over time. And so of course you'd say that like every cell. So this is like a finite version of a differential equation where instead of derivatives, you talk about how like each cell is you just take the average of these 4 cells, and like take the average temperature of these 4 cells, like, and then take that number and add it to this, and then divide that by 2.
Right.
So because you don't want to instantly change, or I think you could also do it the other way. There's names for all of those methods. I don't know what they are, but anyway. And so this one would not change. This cell though would change to, well, it depends how we did it. Let's say we ignored there's no like momentum in the temperature or anything, but it's just like, so this would be like a quarter of this would be 25 degrees, and this would be 25, this would be 25, this would also be, this would be 0 actually. So that would be a little silly. I don't think that really makes sense. Anyway, you know what I mean. So, so on a grid, it's actually not that complicated to do it. You just have to put a loop, and you just have it measure each of these things. The hard part is obviously like getting it to loop over all of the things and getting it to like calculate it the right way or whatever. But anyway, so that's how you do it in in MATLAB in 2 dimensions, but the differential equation, now let's see if I can figure it out based on the thing I just said. dt is, I don't remember. Actually, let me just look it up because I kind of want to, I don't think it's really not that complicated. It's a first order differential equation. Okay. All right, never mind. I'm having trouble finding it. Anyway, it's not important. I'll send everyone a video about it because there's a really cool video about it, which just shows a visual example in 1 dimension of like something's really cold here, like if this is temperature, and this is X. Something's really cold here, and then it's really hot here. What happens when you run over time, and you'll see it goes like this, and then it goes like, you know, that, and then it's like over time, and kind of like literally exactly how you'd imagine it would work. I mean, you know how hot and cold things interact, so of course. Anyway, okay, so does that make sense?
It does.
So the biggest thing was just the using, we're going to use average power, I guess.
Okay.
Okay.
And then, you just solve for time. Okay, that makes sense. And then what was Ron saying about water?
So he was,
That's
and the one about, so you,
B24, 24B. Assuming the water boils away. Wait, no. Yeah.
Yeah,
it
20. Yeah,
produces
sounds right.
Instantaneously, and 5 grams of water at 20 degrees C.
So right, and so I think the temperature. You know the average temperature of the aluminum, right? By this point in the problem.
I believe so.
So you have MC delta T. So this is all aluminum. And then this is going to be equal to, we've done this type of problem before, going to be equal to the, oh, actually, hold on. Yeah. So the heat, this is the heat lost by the aluminum. This is going to be the heat gained by the water from, I think it's at 20 degrees, right? So it's liquid water.
Okay.
Right, and this is going to be, this is 80, right?
Right.
Kelvin. But then, sorry, you don't necessarily know that it's going to boil. I guess you would have to solve this. So this is for, I'm writing M and M, but this is M of aluminum, and this is
M of water.
Water meaning liquid, obviously.
Right.
So you don't necessarily know right away what's going to happen. It might not, does it say it's going to boil?
Assuming the water boils away quickly.
Okay, never mind. Okay. Forget everything. So you do know it's going to boil.
Yeah.
Let's say they gave you the problem, but they said you put water on it, what happens?
Right.
What's the final temperature? They could just say what's the final temperature of the aluminum, because you don't necessarily know
that it boils.
Right, and it actually doesn't even matter if it doesn't matter to the aluminum if it boils. Like whatever happens when it's at equilibrium, or whatever. So you might end up being where, some of the heat. Of course, you would have to say when does the water become the same temperature as the aluminum? We've done that problem before. But they say it boils, so we know that clearly there's another term that looks like ML. This is going to be vaporization of water. This is the same mass of the water. And that's it. And then we don't have now, if we said, let's say it was trapped and it heated up the steam or whatever, or the vapor, then of course we have the other MC, when we do these problems normally we have like the ice melts and then it warms up the water.
Right,
So,
like
but in this case I think it's pretty obvious that we don't want to talk about this the vapor anymore.
It doesn't talk about the vapor.
Right, because it seems like it would just boil and then in normal environments the vapor is not going to be
Contained.
heating up from it's just going to be escaping the atmosphere. So we don't have any other term here. So this should be the whole thing. Now this is in the solutions, and the only thing that Ron was asking is he just got an answer of 80 Kelvin, as he got an answer from delta T is, I think it's his answer is delta T is 80 Kelvin, and the answer of the aluminum. So that's the change from, I forgot what it was, but it's whatever.
Mhm.
I guess so it's decreasing because this is the what he lost.
Right.
The answer key says it's like 7.5.
Mhm.
So I don't know. That was his question. So I don't know because I haven't done actually the math. Did you do this one yet, or
Yeah,
not
I
to call
mean,
you out? But
no, I did. I
Okay.
like did. I put in like the numbers, but I don't have my calculator with me.
oh, okay,
so
that's fine. So anyway,
I've like set them up, but I haven't like done
right?
them.
Okay, fair enough. But the thing the only thing I care about
Mhm.
is that this formula is actually correct and that people understand
Mhm.
what it's doing and why. We could even set this up as I think I'm sort of anticipating people being confused about this. I don't think no one's ever said there,
Mhm.
and maybe they're not. But if you wanted to write this as for example, how do you know that this delta t is going to be negative?
Mhm.
Now, delta t is just the change, but how do you know this should be a negative thing that should go down? Because all you have is 80. How do you know if it goes up or down? Now, obviously, we know if this heats up, this is better cool down.
Mhm.
That's how it works. But how can we write that in a more sort of why should you have to remember the signs are different? Why is this delta t
Intuitive way.
right? Why is this a positive number that means it goes down, and this is a positive number that means it goes also down. Wait a minute. Oh no, it goes up. I'm sorry. What am I talking about? This goes up because this was charged at 20.
Right.
Well, okay. So the reason is because we're not keeping track of signs very well. The true way we should write this is conservation of energy. This says that the change in energy of a closed system is 0,
Mhm.
which is written as Q aluminum,
Mhm.
right? Minus, or actually, sorry, I want to write minus Q aluminum plus Q water is equal to 0. And Q water means the whole thing.
Mhm.
Water it's all water, but it's being vaporized. So the heat is being given up by the aluminum, and now the delta T is, you can just put the minus sign inside the delta T, and now it means the delta T is losing heat. And in this case, it's a positive Q, so delta T is getting it. If you want to say, now if you write it this way, which is sort of more correct, and then you move it over,
Mhm.
you should get exactly this. Anyway, I don't know, I have several minus signs in my head. I don't know, for some reason they're not. Anyway, don't use your intuition.
Okay.
The don't was for something else. Use your intuition. Use your intuition because it's the same thing. Remember in last semester when we were doing the gravity problems, and I was saying oh, so gravity is negative, but that means that downward is negative, and so all your velocities. You could do all that, and that's fine.
Yeah.
But a lot of times you can just
you move the gravity to which way is
you could just
positive
right, or you can just kind of use your intuition as a ball falls this much, and if you get a minus answer,
Mhm.
you're not gonna be like, oh, I guess it went up. No, you're gonna obviously it went down. So sometimes by hand you can do, or if
Okay.
if a ball was being thrown in the air,
Yeah.
and you know that gravity is downward, and then
Yeah.
you get two terms in your equation
Yeah.
that require you to add them,
Mhm.
two terms for the position, and you add them together, you might be like, well, that doesn't seem right. So if this is your gravity term, and this is your velocity term,
Mhm.
and you get a bigger number, this may be a little too abstract because I haven't written it, but you know what I mean. Gravity should be making
It go down.
and velocity is making it go up.
I see what you're saying.
And so if you get that they add them, you might literally what I do when I do these problems is everything's positive. Every single thing is positive. And then later I'm just well, obviously this is that. So upward is positive. I mean, this is all, by the way, a formula for x. I should mention that too. Anyway, you don't have to do it that way, obviously. But I just mean for these intuitive things, you shouldn't be thinking of aluminum and water and then writing an equation, then mindlessly solving equations. You should be thinking of I'm writing a thing about cooling aluminum so that water heats up.
Mm-hmm.
so that you know that you don't have to ever worry about the sign of this. You can just say, I know it cooled down to 80 Kelvin. Sorry, I don't know why I wrote 80. Oh, he got 80. Actually, let me think about that. It's confusing me because it's the same as this is not the same as this 80. It's
Okay.
different. I mean, this is for the water, because the water started at 20 Celsius and went to 100 Celsius, obviously, because that's when it boils. And so this 80 Kelvin for that. This is just what Ron. I don't mean to. If this is wrong, I'm sorry that I'm embarrassing him now by calling him out for. I don't know if it's right or not. I'm just saying like the formula that he set up and that the answer set up also, the same way, are correct. And as long as you plug in all the, I mean, if you plug in the numbers and you mix up the M's or whatever,
Mm-hmm.
I don't care at all. I don't even.
Wait, wouldn't it be 80C, not 80K?
Well, delta T
Oh, right.
is the same.
Okay,
Yeah.
never mind, yeah.
C and
Sorry.
yeah. I always write K because the units of
No,
SI units are all in K.
You're right. I forgot it was like delta is the same.
Yeah,
when
delta
you
is the-
subtract it all.
exactly.
Don't
That's
worry
the
about it.
that's the
It's
nice part.
my head being.
That's how they just constructed Kelvin actually.
Yeah.
They said, well, we want 0 to be 0, but we don't really care what like 1 is. There's a
Great.
there's probably some really annoying units where like 1 is like freezing water, like 0 is absolute 0, and then 1 is like freezing water,
Mm-hmm.
and that's it. And then you just go, and that's like an incredibly bad unit to use. But anyway, whatever. That's something that like a physicist would do, I think. Be annoying about that. Yeah. Do you have any other specific questions?
Don't. It kind of made sense.
Okay, because I wrote down a few things just from the last slides that I was just gonna.
Well, let's do it.
I wasn't gonna like go over everything because you can just look at the
It's a
slides.
nice
and
day
it's
outside.
pretty, and it's a nice day. But I'll just talk, there's a few things where I was like, I don't know. I was a little confused by, and so I thought this is something I should talk about. There wasn't very many because it's pretty clear in the. There's like one slide for each thing
Mm-hmm.
in the well, besides the heat engine stuff, but for the heat transfer stuff. So we have. Well, we kind of already wrote this, but for the conduction, we have KTHA dt dx. We already know that. I guess the biggest thing was that KTH, what is in watts per meter Kelvin, which we know because A is in. Wait. Yes, because A is in meters squared.
Mm-hmm.
This is in meters on the bottom, so it cancels, so it's just 1 meter. So there's 1 meter on the bottom here. This is in Kelvin here. The answer has to be in watts, so that's it. And the important part that he wrote was that metals. So K tells you about the thermal conductivity. I think that's what it's called actually. I didn't even write that. That sounds like that's what it's called. I think it's called the thermal conductivity. But what's interesting is, which I actually literally didn't even know until I read. I think I was in class. Maybe I wasn't. Anyway, is that metals? Obviously, we know metals have a high thermal conductivity. We know they have electrical conductivity. We know why with electrons. You learn that in chemistry and stuff. But why do they have a high thermal conductivity? And I just thought, I don't know, the electrons kind of move around to help, right? And that's actually basically exactly right. Okay, I guess it's not that surprising. But what's kind of cool is that for metals, the heat transfer is done mostly by the electrons. So the electrons in the conduction bands literally gain energy, and then because it's such a good conductor, if you have a metal and like let's say you have like a big ball of metal, and like you put like a flame or whatever on one part of it,
Mm-hmm.
those electrons here, well, they're not going to want to, just like the entropy, the equipartition theorem, where if you just look at all the configurations, this is very unlikely that all of them will be here, so they tend to spread out. That's the second law. Or you can just use these equations for like how heat dissipates stuff. But the heat, because like how does the heat get from here to over here? Well, if the heat is in the electrons, if the electrons literally are have higher thermal energy, well, electrons can just move wherever they want. So they will just move away. I mean, it's just if you heat it's just like convection when you heat water, the hot water will rise and then will dissipate and will want to give its energy to other things to heat up the whole thing. The only reason it wouldn't do that is if it was very hard to transfer the heat around. But in a conductor, it can't possibly be hard to transfer the heat around because as long as the heat is in the electrons, and it's just that happens to be the case.
Okay.
If the heat is in, of course, some of the heat is in the other electrons, the non-conduction band electrons, but enough of it is in the conduction band that it's fine. So anyway, so the metals are good conductors. That's essentially the explanation. So essentially the statement I would say is the metals are good conductors because their heat is stored in their electrons, which can move very freely. So therefore heat can dissipate across the surface very easily. Insulators, which don't have those types of things, like don't have electrons that can move around, are not obviously good conductors of heat. But the reason is because, well, it's the same thing. It's just because the electrons can't move around. So where is the heat? Well, it's just in the non-conduct. When I say electrons, by the way, I sort of implicitly mean the conduction electrons.
Right.
The other electrons also have heat, and they just sit around. So in an insulator where there's not a strong movement of electrons, the heat primarily, sometimes, but usually gets transferred through phonons, right? Because phonons are literally if you have like a lattice, right? So a lattice is not a metal because the electrons don't look like this. But in a lattice, let's say this site here, so again, the reason we're not talking about electrons here is because they can't move freely, so they don't really matter.
Mm-hmm.
But the heat is in like these nodes, and remember the modes of, when we do the equipotential theorem, the modes of oscillation, the modes of energy are it can be moving in the x and y direction, and z maybe, and it can have these spring constants, right? So you can have the 1/2 k x squared, plus 1/2 mv x squared for a one-dimensional example. Of course, 2 dimensions is the case. So if they get vibrated and then another one vibrates too, because it receives energy from that, the energy that got transferred from here to here, this energy is a phonon, right? That's it. So, and the thing is that phonons don't transfer very efficiently compared to electrons. Electrons can just move.
Mm-hmm.
It's like if someone had like a coronavirus and just went to another country.
Way to make it relevant.
Yeah. You're welcome. It's topical. So next year when people watch this, they'll be like, What are you talking about? But no, but if you could move the electron that's hot all the way to the other side, well, it's going to heat up the other side very efficiently. It's going to distribute really efficiently. But if you can only infect your neighbors with this heat, or you can, because phonons, you'd have to look into the properties of phonons, and I don't know too much about them, but they're not as free-flowing.
Right.
It's not as easy to flow. It depends on the spring constants and all that stuff.
Mm-hmm.
They're not as free-flowing, and they tend to just excite their neighbors, and that's why you might get a local, the heat would spread locally and slowly.
Like
miles.
Yes,
exactly. Right. You need to have a strong spring constant, so to speak. Yeah.
Jesus Christ. Sorry to everyone on the video.
Exactly. No, that's very helpful. Thank you.
Anyways, moving on.
So those were the points that he wanted you to know.
Okay.
Also, Diamond
Oh.
has like ridiculously Diamond. I don't know why. Diamond has a ridiculously high K.
Okay. Oh, there you go.
And that's not a conductor of electricity.
Right.
Because it's not a metal,
Mm-hmm.
obviously. But it just happens to have a crystal structure. Of course, they can't stop talking about the crystal structure of diamond. It's interesting for a bunch of ways, I guess. Anyway, but it's such that phonons apparently travel really easily or something. Or, I don't know, whatever. Each thing only has 3 neighbors, I think. Each, lattice point has 3 neighbors, which is very low.
Mm-hmm.
Most lattices, if you imagine just a grid, like a 3-dimensional grid lattice, that would have 6 neighbors. I had to think about it, right? Because there's 2, there's 1 up, 1 down, left, right,
Mm-hmm.
forward, back.
Oh, yeah.
So, and you could have more complicated ones, and you could have a tilted version of that, and that's much more common. There's those, or hexagonal lattices,
Mm-hmm.
and you might have 6 neighbors or something. Having 3 neighbors, I think it's 3. It's either 3 or 4, but I can't really draw. It's like a tetrahedron.
I know what you're saying.
which is actually, so something like this.
Yeah.
Which is actually, this is a tetrahedron, which is, if you, I can feel the tangent beginning to start. There's a thing called platonic solids,
Okay.
which is really, you should look up if you don't know much about these platonic solids. This is purely math. There's nothing physics about this, except for, I guess, crystal structures.
Okay.
But platonic solids, there's 5 of them. The definition is it's a 3-dimensional, it's called a polyhedron.
Mm.
This is called, a polygon is this,
Mm-hmm.
right? A polyhedron is a 2-dimensional one, or it has surfaces.
Right.
It's in 3 dimensions, and all of its surfaces are regular polygons. A regular polygon means all the sides are the same. So these are the regular polygons. I pretend those are the same.
Okay.
And then there's a 6, and obviously, so there's obviously no 2, so it's just 3, 4, 5, 6, etc.
Mm-hmm.
These are the regular polygons. And a platonic solid is when they all have the same one. So if you took 4 triangles, you can actually make a solid where all 4 faces are the same regular polygon. So this is called a.
So like that.
So this is one. This is called a tetrahedron.
Mm-hmm.
You can also put 20. Sorry. You can also put 20
Mm-hmm.
triangles in a certain way. That's called an icosahedron.
Oh, wow.
You can also put 8 of these and make an octahedron, which it looks kind of like 2 of these. It's not quite, but it looks kind of like 2 of these stacked. You can put 6 of these and make a cube. You can put 12 of these and make a icosahedron. And guess what else you can make?
What else can you make?
I named 5. There's 3 with these,
Mm-hmm.
1 with these, 1 with these. Guess what else you can make? Nothing. That's it.
Oh.
There's 5. You can prove it, which I could do if you want. I don't have to do it, but you could do it by looking at the internal angles of these. That's how you do it. I'll just give you the hint. Internal angles, and if you try to stack 2 triangles, what is the internal angle now? You know, if you make the internal angles of a bunch of triangles 360 degrees, if you put 6 triangles, 6 regular equilateral triangles,
Mm-hmm.
you make 360 degrees, but you can't make a closed surface with a 360 degree angle
Right.
because the angles have to be smaller than 360. So anyway, and that's why you can't make any with a hexagon because you would need 3 and it would make 360. These are smaller than, like, you could put 3 together and glue them, and you'd actually have to make 20. That'd be fine. You can only do 3 of these. Like, put 3 and that makes a cube.
Mm-hmm.
You can do 3 of these, 4 of these, or 5 of these, and that's the tetrahedron, octahedron, and icosahedron. Anyway, so why do for diamond. So in some sense, diamond has like the simplest crystal structure of it's like mathematically one of the simplest, sort of most sparse crystal structures. Each one has a very limited connection to the other ones. Now, why does that make it a very good thermal conductor? I have no idea. I'm not even totally positive this is correct for diamond. Anyway, so let's move on. But this is really cool. I'm sure if you Google this, you'll find a bunch of stuff. But there's YouTube videos, there's definitely YouTube videos where people prove this, that there's only 5%, because it's not a super, I kind of already told you the answer, but like someone can actually show you more visually. And it's actually kind of a cool proof because it's like a mathematical statement about shapes that you hopefully are familiar with these shapes.
Yeah,
Okay, just make sure.
Before.
I didn't want to use terms like square without defining them, but
right over my head.
But anyway, those are the 5 platonic solids. What's interesting is if you go to 4 dimensions,
yeah,
those are called polytopes. Polytope means any dimension.
Okay.
So these are all polytopes as well. But a 4 polytope, there's actually infinitely many. And in 2 dimensions, there's also infinitely many, right? Because you can, just put n sides, which is interesting. But like a 4-dimensional shape whose boundary is only 3-dimensional tetrahedra, you can make that, and you can make it for anyway, it's a whole thing. So there's something interesting about 3 dimensions with this platonic solids.
I just had like a flash that I was in an Interstellar movie and you were trying to explain gravity to me.
Yes.
I was like, oh god, I don't know what this is.
What was that stupid line from that where Anne Hathaway? It's Something about love. That's really stupid. In that
Oh, it's
movie.
like continuous and gravity are the only thing. I don't know. It's
God.
time. I
Anyway,
don't know. Yeah, it's been a
That's-
while.
I remember that line because it was
Clearly.
yikes. I was like, are you serious? Anyway, it's a good movie other than that. It's fine. Okay, and I was gonna write what is in 3 dimensions. It's not. It's the same thing but with a gradient instead of a derivative. So I won't write that. And then we have the Stefan Boltzmann law, which is actually really like important in physics. Which is for radiation. Of course, you've used this many times in the homework and whatever. But
Mhm.
I just want to point out the important parts because, of course, just using it is fine. But things you might need to remember for like a quiz.
Mhm.
Not again. I don't mean to. I always sound like I'm giving a hint, and I actually genuinely have no information. So
Just life in general.
yeah, life in general, which is not tomorrow. First of all, we don't have class tomorrow, right?
What? Yeah, we do. Oh no.
I think it's Thursday.
You don't have class tomorrow. Okay.
Oh, you have. I'm sorry. Of course you have.
We do have.
I'm not coming.
Yeah, no.
No, you have the other class. Sorry.
Yeah.
This class doesn't meet
We
until
don't
Thursday,
have physics tomorrow.
Yes.
Correct.
and then the quiz I believe is next Tuesday.
Tuesday.
Okay, just making sure because
Yeah.
someone was worried it was tomorrow,
It
and I
is.
was like, I don't think so.
There's another week.
So what's really weird about this is that there's a 4th power of temperature.
Mm-hmm.
Please, if you're curious, look it up on Wikipedia. They will have a derivation in terms of Planck's law. Anyway, you don't have to do that. There's no reason to do that. But
In all my free time.
in all your free time, it's not super interesting. But it's kind of a weird thing because normally in like physics, like with gravity and projectiles, you never have a 4th power of anything. So it's kind of a weird thing. I always thought that was kind of interesting. But anyway, this is called the Stefan Boltzmann constant, I think it's called. Anyway, it has units of watts per meter squared per Kelvin to the 4th, obviously. We know that's obvious because we know that E has no units. So this is the emissivity. I think I put another M. I don't know how to spell it. But anyway, something like that. I think there's only
I
one
think
M.
there's only one.
And it's just a number between 0 and 1, right?
Sounds right.
It's never more than 1, because 1 is a black body, which is like sort of almost like a perfect absorber and emitter. And that's it. And then A is, of course, surface area, not the actual, make sure it's surface area, of course, which, of course, the only reason you really need to use that in these problems is like with a sphere in the desert, which, okay, I love when they're all going to be spheres in the desert, don't worry. But in a sphere in the desert, if half of it is exposed to the sky and half is exposed to the ground, so you just need to make sure you do that. Take the full surface area and just divide by 2 to get half and half. So I'm sure you've already done that.
Yeah.
And then T, of course, is the temperature of whatever. But the important part is that while everything emits radiation based on its, so you can see that the only way you get 0 emission is if your temperature was absolute 0. It's literally the only way. This is always positive. These numbers are always. This is a constant. This is always. I guess if E was 0. I don't know what material that would be. That would be like a really weird material where it doesn't emit anything. Anyway, that's not going to be 0. A is always positive unless
There's something there.
Exactly, something there. And then T to the 4th is clearly always positive. It's never negative, of course. So P is always going to be positive. So if you put something in space, right, where it just sits there and it doesn't receive anything, or you put something in a box that's like, there's no conduction, it's isolated or whatever, and it's in a black box, it will just emit radiation. This is called thermal radiation. That's a T. Until it cools down literally to absolute 0. Now, of course, that's an ideal thing and never, blah, blah, blah. So, but that's kind of an interesting thing. And the only reason that you might think, why doesn't, like I go to bed at night and there's no lights, like, why wouldn't I cool to absolute 0? Obviously, conduction is way more important in that situation. There's a million answers of why. But the one I was looking for, what I'm trying to get at is that P, there's an absorption, and this equals P emission at thermal equilibrium. So all that means is that when an object is at, we've been saying objects are at thermal equilibrium when their average internal kinetic energy, called temperature, is equivalent to each other. And then there's like the zero flaw or whatever of thermodynamics that defines this or whatever. But we can actually define it just in terms of radiation. So forget about conduction, forget about even what it's made of, even the molecules that it's made of. If you accept the sort of basic quantum mechanical principle that is kind of unrelated to the other ones that we've talked about, but that everything radiates energy proportional to its temperature to the fourth, then you get that every object in thermal equilibrium radiates energy exactly as much power as it receives. It doesn't necessarily have to be the same, wavelength or the same anything like that. Well, actually, no, it does have to be the same, but that's a whole separate story. Because we don't have wavelength anywhere in here. But you get that they're emitting and receiving at the same rate. And a consequence of that is that if you pretend this is an absorption one, this is actually going to become not the emissivity, but the absorptivity or whatever. Absorbativity. I believe it's called absorbativity.
Okay.
But anyway, they write that as alpha, I think.
Yeah.
Alpha. So for the, it's in the notes. There's an yeah, and in the book right before the questions and in his notes, there's the same problem done, which is the sphere in the desert,
Right.
where half of it is exposed to the sky, half of it is exposed to the ground, and there's also another, there's kind of technically an alpha here too,
Alpha tank.
which is only when you're talking about power absorbed, because if you don't do this, what you're actually to find the temperature of the tank, what is done in the problem, which is, they kind of did it all out, but you find the power radiated by the tank using its temperature, then you find the power radiated by the sky using the sky's temperature, and then the surface area of the tank, but we're not really, that's all if we plug in the emissivity of the sky, which they say is 1, and sigma is a constant, that would give us the power radiated by the sky onto the tank, but it doesn't tell us how much of that is actually turned into thermal energy. It just tells us that's hitting the tank. Some of it might be reflected, right? So in other words, some of the sunlight is reflected. What is that? That must be the alpha term here. So we have the alpha term. So really, it should be like alpha times epsilon should be a whole quantity. And where this is like, it's like epsilon for absorption. There's a P here. It turns into a P when I don't know why. English is weird. Anyway, so when you're talking about emitting radiation and you don't care when it's absorbed, you just have this equation, right? The tank emits energy. We don't actually care where it goes. When we're talking about something being absorbed, we don't necessarily just care about, we care about the emissivity of the sky and the temperature of the sky, but the surface area is of the thing we're considering, and then the absorption, it's basically alpha times epsilon kind of thing, where it's really alpha, remember, is just actually epsilon for every material. So alpha of the tank is just epsilon of the tank. And epsilon, so the other epsilon, which is this one, when you do that part, is for the sky, which is like 1 or whatever. So that's the reason why, that was just when I read the problem, I was really confused by the alpha for a while. But that's basically where it is. It's when you're talking about radiation and absorption, basically transfer of energy from one place to another, you have to include both the emissivity of the material of the thing that's radiating and the absorptivity. I didn't even write it because I don't know how to spell it, of the thing that's getting the energy. So you could, in other words, you could think of that as the tank is reflecting half of the energy that it receives. So that's it. And and then just of course make sure that for the sky and the ground, that when you use alpha, you divide the surface area, which is like 25, you divide it by 2. This is just for the specific problem in the thing. So I don't think you have the same type of problem, but for that problem, it was like a spherical thing, so you had to divide it by 2. So
water tank.
Right, and if it was like, let's say, a disk, I don't remember if this is a homework problem. Actually, I don't think it is, but if you had like a disk, a flat, thin disk, let's say it's very thin, and it was in the desert, for some reason.
It is something like that.
There was something with the disc, but I just mean like you had the same problem of a water tank in the desert, but it was a disc instead of a tank, like a settled sphere. I mean, anyway, if you just had it in the desert, I guess it would be the same thing because half of it would be emitting to the sky and half would be emitting to the ground.
He just has an aluminum plate heated by an electric heating element with the top radiating to the sky and the bottom radiating to the ground.
Oh, okay. So okay. Well, that's all I was trying to say is that the
Plate.
top radiates. I guess that's kind of obvious now that I
Right.
say it, but yeah. So okay, fair enough. Yeah, that's it.
Okay.
That's all I had.
Cool. Well, you answered my question.
All right. Well, what else? Anything else?
I know I usually come in here with lots of questions, but that's it.
No, I think this chapter, we didn't go deep into these things.
Right.
And the heat engines is kind of the main thing that we went deep on, but
They're engineers, of course.
yeah, some people are familiar with them, very familiar with them, but also they're kind of done a lot. But then the other parts, like radiation stuff, were like you have to know like one equation,
Mm-hmm.
and then the problem is like do use that equation. So I don't think most, and then some of them are using the heat things that we've done before.
Right.
Was there a problem where they said, I can't remember if I just read this and it was not a homework problem, but like they said that they're like ideal gas is put in a tank and it's heated to, oh, okay, that was a heat engine problem.
Where's he put it? That was even one we just had to do, I think. Where is it? Oh, yeah, 15, 1 mole of an ideal
Oh, yes, yeah,
atomic
okay.
gas, an equation of PV equals RT begins at a pressure of 1 times 10 to the 5th and a temperature of 300 Kelvin and is taken through the following cycle.
Yes. Oh, okay, and it's sort of done in the notes, I think. Yeah, you use PV with RT like a few times.
Yeah.
Okay.
Mm-hmm. And then how much net work is done and
Yeah.
the heat added, all that fun stuff.
Yes. Okay. So that hopefully, using last week's,
Yeah, it's like a whole cycle.
it's a cycle, and you can break it apart with the columns and
Yeah, that's what I was
Okay.
thinking of doing.
All
Once
right.
I get my calculator back.
Excellent. And when is this due? I forgot. Tomorrow?
Is it due tomorrow?
I mean, it could just be Thursday, I guess.
I don't know. I'll bring it tomorrow.
Is this homework 6?
7.
Oh, 7. Okay, that's what I thought.
Yeah, we just turned in 6.